Welcome to our presentation. I am Çise from Industrial Engineering Department, and my teammates are Zeynep, Arda, Eray, and Seyit. Today we are going to present exploratory data analysis of our dataset. Here you can see the content of our presentation. First of all, we start with the brief description of our dataset, and then we will summarize our data. And we did some processes in order to clean our data in the third part of our presentation. You will see the data cleaning that we did before. And after these processes, we face with the imbalance data set situation. And in the fourth part, you will see the how we deal with this situation. In the fifth part, smooth application will come, and the last part of our presentation we will conclude, and we will be waiting for your questions.
I'm Eray Bedir from Information Systems Engineering. Our dataset is from Kaggle, from someone called Stefan Matska. Our dataset was created synthetically. They include the milling machine statistics like air temperature, torque, tool wear, machine speed, and they give if the main fails or not. If it fails, what type of failure it will give. Next slide, please. Our aim is here to detect if a main is going to fail or not, and if it fails, what type of failure it will give. Our motivation for it to minimize downtime and save on maintenance cost, also extend the life of aging machines. Next slide, please. We will use supervised learning method because our data is labeled, and we are going to use multiclass classification as we are going to predict failure type. This has 5 values, 4 of them are failure types, and 1 for the most state of no failure. Next.
I would like to reintroduce our dataset before it has been processed. So our dataset has 10K samples with 13 features, 7 of them being categorical and 6 of them being numeric with 1 metadata. And we had no missing data in our dataset since it was synthetically constructed. Next slide, please. And as you can see over here, the instances of machine failure being, well, the machine not failing and the machine failing is severely imbalanced, with the failure rate being 3.39%. And as per what our instructor has told us, we have to fix this imbalanced data set, and this is what we will be mostly focusing over in the next slides. Next slide, please. And again, these are the features of our data set, which includes the product ID regarding the quality of the machine, the type of the machine actually, sorry, and the air temperature in the surroundings, the process temperature that is inside the machine, the rotational speed and the torque of the rotating parts of the machine, the tool wear of these parts, and a machine failure label, which indicates whether the machine has failed and what type of failure it has. Thank you. So you are muted.
I'm sorry. Here I will talk about data cleaning that we did. First of all, we start with the UDI feature that is an unnecessary feature for the prediction since it has no effect on the prediction. We remove that column, and no other columns were removed, but we modified the columns. You will see later. Here at the left bottom part of the page, there is a table which contains machine failure and the failure types. In 9 instances, we had machine failure, as you can see the ones in the machine failure column, but we don't have type of failure, as all of them are 0, you can see. And in 24 rows of our data, there are more than 1 failure. For example, in the first row, as you can see, in the right part, toolware failure is 1, and also overstream failure is 1. We don't want that situation in our dataset, so we deleted that 24 rows from our dataset.
Excuse me, Çise. I didn't understand this part. Can you explain more? I didn't
Okay,
understand.
sure. In our dataset, there are 24 rows with more than one failure type, actually. And in the prediction, it may occur confusion. We thought that, and that's why we deleted that 24 rows that has more than one failure type. We removed from the datasets.
So do you mean in the right side corner, right? The blue
Yes, right bottom.
Yes. So these blue lines are examples from for the 24 rows, right? With more
Yeah,
than one failure.
just 4 of them.
But why did you remove? Still, I couldn't understand. Because you are gonna predict if failure occurs or not, right?
Yeah.
You're gonna predict the failure type as well.
Actually, we are going to the model will predict if a failure occurs and what type of failure occurs. We have 5 of the 5 different target types, no failure, and the others are the failure types. I mean, toolware failure or power failure or overstream failure, etc. I mean, we have.
I understand you. But in reality, do you know the domain? Do you have the domain knowledge about this data set? I mean that is it possible that a machine can fail for the 4 types of failures or 5? I don't know. Is it possible in real life?
Actually, for example, if a power failure occurs, there are some features like air temperature, process temperature, rotation temperature, and they have some values, and then a power failure occurs. That's why while
I would like to ask that in the 24 samples,
yeah,
do you think that there are some kind of error, or do you think that it is the factual value? Maybe sometimes a machine can fail due to many reasons, like the engine failure and I don't know the other failure type, but one of the other failures. Is it possible that because of 2 failures occur at the same time? Is it possible or not in real life?
Can I answer, teacher?
Yes, please, Eray.
We didn't have any explanation about it in the data sets, so we figured out that it could be an error. So we deleted that information.
Okay, but you already have an imbalanced data set. If I were you, I was very cautious about to remove some samples from the minority class samples. I wouldn't remove this because they are very, very low number.
You're right, teacher, but we didn't have very explanatory thing about it. We will consider it as you say.
Yes, please consider it because it's not a good idea. 2 reasons. The first reason, in reality, it could be because a car can broke, for example, for many reasons. Some of them, they can occur at the same time, right? For example.
Yes, you're right.
The second one, you already have very, very few number of error or whatever the failures samples. And if I were you, I wouldn't like to remove this. And for your model, it's not, of course, it's not gonna be multi-class, but multi-label. You need to design a multi-label classification model. Of course, in that class, in 468 class, I don't cover the multi-label, but if you like, I can explain it in the class. It is I think that it's not multi-class classification, but it's gonna be multi-label classification. But keep in mind that for the next presentation and until that presentation, please work on it that maybe it's not good idea to remove these 24 samples. Is that okay?
Okay, teacher.
Okay.
We will check it.
Okay.
As you said, it's not an error. We will tell you about it.
Please continue. Sorry to interrupt because it is important.
No,
Okay.
it's not a problem. Thank you.
Sorry. Let's continue.
Hello, my name is Arda from Computer Engineering. After we cleared failure data table, then we start to clear our not failures data table. To do this, we checked our error types one by one in the not failure data. As you can see on the right, there is no data of any error type except random failure. So they are clean data, but in RNF, we have 18 rows that show RNF, but not machine failure. It doesn't make much sense, so we deleted them. Next slide, please. In total, we removed 51 data points from our 10K samples.
But
so
may I ask a question?
Sure.
So
Sure.
You are removing from the still failures, am I right?
Yeah, you're right.
Yes, but they are RNF, but not machine failure. I mean, actually, it's not failure.
But you are saying that 51 samples were removed. And they are
Yes.
all failure samples, right?
Hocam, from the previous slide, actually, when we were talking, like the machine failure being zero is one. And
in here,
in our imbalance, we're having like the machine failure being 0 cases a lot, and we're having the machine failure being 1 cases really low. So these 18 ones are actually still being included in the like, since the machine failure is 0 in here, they're included in the majority class technically, like that. So
Yes,
I think that's not a problem.
One of the failure type, am I right?
Yeah.
Also, hocam, yani,
right.
the random we also thought that random failure, we cannot predict random failure because it's random essentially. So,
but do you understand my point? RNF is one of the failure types, am I right?
yes, hocam.
You're right.
Yeah.
Then you need to fix this mistake, typo in your data. Just make the machine failure 1. Am I right?
But
Yeah,
hocam,
we
you're
didn't
right.
consider it like that.
Hocam, distribution of RNF is not suitable for using. So we think that we can not use it. We cannot use any data oversampling method for RNF. It's not meaningful.
I am just saying that in your data, definition of the RNF belongs to a failure type. Am I right?
Yes. Yes.
If it is a failure type, if it is 1, it means that on the first column, there occurs a machine failure. Am I right? Do you follow me?
Yes.
Yes.
But it is 0, it's a mistake, right? It's a typo.
Yes.
If I were you, I just check, update the machine failure for these 18 rows, make the machine failure 1, and use the data. Why I am deleting these 18 rows from the data set and they belong to minority class?
You're right, hocam. We didn't consider
Sorry, we got
it
your
like that.
point, but since, as Zeynep said, we decided not to use RNF as a failure type because it is hard to predict this type of failure. So if it was a different failure type, maybe we change this zeros as 1, but since it is RNF and we decided to remove that failure type, so we choose the remove all that data.
It is not very often that we are deleting from target values.
Yeah.
Now you are saying that at the beginning you have 4 or 5 types of failures, and you decide that delete one type of failure from the target set. It's not common. Then assume that you have a boss. Your boss will ask that if my machine fails because of RNF, your algorithm will never predict it. Am I right?
Yeah, you're right. Yeah.
But you cannot say yes.
Hocam, we
your
deleted
model
totally.
is useless for that problem. Do you understand? We can remove the feature, we can add new features, but you cannot remove targets.
Yeah.
Assume that you want to predict the flight ticket prices, then you are saying, oh, I remove it. So what are you gonna, I don't predict the prices. So what are you gonna do? I don't like that price. You cannot say this. Do you follow me?
Yeah, you are right. We will fix it.
Yes, hocam.
Okay. So it's strange for me. Think like that. You have the minority class as failure, and you are always deleting from it. It's not good approach. No, it's not wise. Okay, let's continue, but fix this. It's very crucial.
Okay.
You cannot continue with that. Okay.
Okay.
Please continue the presentation.
So we can skip this slide actually we talk about. We cleaned our data, and in the beginning our target was machine failure, but we changed our target because we have 5 failure type feature and 1 machine failure feature. Because we want to find if machine is fail or not, and also its type. To manipulate our target, we concatenate our clean data. You can see on the left bottom. And we use source identification and create a new column which contains all data types and cases where the machine does not give an error. Orange give weird names to our new values. So we changed the names using edit domain widget. After that, we remove the individual failure type columns and machine failure column. Now our target is the newly created failure type column. Next slide, please. In here, you can see our new distribution variables and new targets. But our work was not finished in here. You can easily see there is imbalanced data situation. No failure values almost 97%, and other 4 failure type only 3% in total. And we need to solve this problem and balance the data. Next slide, please.
So yes, as Arda said, our data set is still imbalanced, and since we cannot collect more data, we need to use the data in our hands to be able to either create new data by oversampling or just delete from the no failure instances. But we decided that, I mean, it's quite obvious actually that undersampling the data would make our data set unusable for machine learning, as our minority class had 339 machine failure instances. If we were to delete from the majority class, we would end up with something 700 data points, and that's not wise. So we decided to do oversampling. Next slide, please. And there are many oversampling methods, but we looked at 2 of them mainly. The first one being random oversampling and the second one being smooth. Random sampling is the simplest one among all of them, and it's used to, well, balance the imbalanced data set. And it balances the data by replicating the minority class samples. And SMOT stands for synthetic minority oversampling technique, and it creates new synthetic samples to balance the data set. Next slide, please. So we chose SMOT technique to oversample our data instead of the random oversampling, because random oversampling duplicates the already existing data from the minority class, albeit randomly, to increase the size of the minority class. But this causes a risk of overfitting, as when you split the data between trained dataset and test dataset, the duplicated values may end up in both of them, both in the train and test data. So this will make the model look better than it is, maybe. And next slide, please. I'm done.
In the end, we decided to use smooth method. Basically, smooth, as you can see on the left graph, draws lines between minority samples. You can decide how many lines it will draw in k neighbors. Like you can, if you give 5, it will draw 5 nearest minority samples lines, and it will place synthetic examples of minority samples between the lines on the lines, as you can see on the left graph. There are many extensions to smooth methods, which you can decide how it will do it, how it will balance it, or will it affect the majority sample or not? Next slide, please. Orange Tree doesn't have a smooth tool, so we had to use imbalance learn add-on to add smooth oversampling method. You can do it on options add-on on Orange Tree, and after that you can use Python script to execute smooth method. Next slide.
Hi, I'm Seyit Cem Yılmaz from Computer Engineering Department. We have two options when using smooth. First one is to equalize the sample count of each categorical data to the highest categorical data. And second one is having 50% no failure data and 50% failure data. The 50% failure data is distributed between failure data types. Next, please. In first choice, we used a little Python script in Orange to use smooth functions from imbalanced learn library. When we do that, we obtain 20% equal data distribution, which includes not failures and failure types. After oversampling, we obtain what was that? 40. Next slide, please. Yes, this one. They are in this graph. It can be seen that all categorical data have a 20%, and these are equal, and totally we have 48.2 thousand data. Next, please. In the second choice, we used again a Python script. The Python script similar the previous one. We modified the previous one to create a different data set. In new data set, we have 50% failure data and 50% not failure data. In 50% failure data, and each categorical failure data has 12.5% distribution. Next, please. In this graph, we can see that no failure category has half of the distribution, and the other ones actually failure types are at 12.5 percentage, and totally we have after oversampling we obtain 19.3 thousand data. Next, please.
In order to see the relationship between the features and the target values, we did scatter plot diagrams, and the difference between the left one and the right one is actually clearly seen, but left one is before oversampling and after one is right one is after oversampling. The right one's amount of the points in the right one, as you can see, is clearly high from the graph. And this is actually about the relationship between power failure and the rotational speed and torque. As torque increases in a low rotational speed, failure occurs, and as rotational speed increases and low torque values, also power failure occurs.
Çise, I am sorry. This is
Yeah.
after which sampling? The 55th or the other one? There are two
Second one
sampling
hocam.
methods you mentioned.
Second one.
The second one.
Yes.
So 50% is no fail, and the 50% is distributed among the 4 failure type. Am I right?
Yeah.
Yeah,
Yes.
hocam.
Okay.
We forgot to mention that, sorry.
Okay, let's continue.
This graph is also about power failure, and here the features are torque and air temperature. Here, as you can see, in the low torque values, air temperature is a significant effect on the power failure, and also high torque values, power failure occur.
Here you can see the scatter plot for heat dissipation failure with air temperature and process temperature. Red dots are HDF, and even there are no failure dots between failure dots, still you can see they mostly gathered in an area, specific area. Next slide, please. And this is for the overstrain failure relationship. You can see in here tool wear and torque, and they also gathered in an area, right corner. And can continue. Next slide, please. This is now we come to the end, and this is our orange screen. You can see all the work we have done and our filtering and Python codes. And this is the end of our slides. Next slide, please. Thank you for listening. Do you have any questions?
Thank you for the presentation. Thank you for fixing the previous feedbacks. Please keep on doing this. So please take notes about the feedbacks that I try to provide during these kind of presentations and improve your presentation. Now, if we go back to 2 slides before about oversampling. Seyit, I have a question for you. Yes, here.
Here hocam.
So
Which one, hocam?
at the beginning of the oversampling, before the oversampling, TWF, HDF, PWF, and OSF kind of failures, how many they have samples in the original data set? How many?
Previous ones have
I
Çise,
mean,
could you
now
300.
they have 10,000. Am I right? Each of them has
Yeah,
totally 10,000.
close to 10,000.
10,000 right now, according to that graph. But originally, how many of them exist in the original data set?
339.
Total, right?
Yes.
Yeah.
Total. On the
Yeah.
average, we have only, if 300 over 4, we have only 70, right? On the average, 70.
Yeah, on the average, yes.
Yeah.
Then you increment synthetic data from 70 original data, authentic data, to synthetic 10,000. What do you think about this, Seyit?
Actually, we fill the blanks in graphs, I think, with using smooth.
Do you think that is reasonable? From 70 to 10,000.
It may be problematic, maybe, but
You are exaggerating the oversampling.
Our input data is not enough, maybe, but we fix it with you.
By saying fix it, actually you are not. You are creating a very, very synthetic data set as well. You begin with a synthetic data set. Now you are exaggerating the oversampling, making some data set that I think, the other members, do you understand my point?
Yeah, yeah.
Yes,
Yes.
hocam.
Actually, teacher, we have searched how much oversampling is too much.
How
but,
much oversampling is too much? That's the question.
Yeah, we didn't
Think
find
about it,
anything
okay,
to
Eray?
okay,
Think about
okay.
it, okay? Okay.
We will
Hocam,
search
I
about
would
it
like to
and
ask
present.
something. So, like, for example, over here we oversampled, right? So, like, maybe if we just cut this to half, would it be okay?
But still, it's gonna be 5,000
Okay, cut that to half
270.
too. And
Think about this, okay? Think about and
Okay,
read
okay.
something
Yeah,
about it.
teacher, I think Zeynep wants to ask if we can reduce after oversampling, or should we oversample less at the beginning?
Less, right? I think.
Okay.
But just search for it in the literature. What is more for oversampling?
Okay.
Okay.
We will present about it.
Yes. So in the 2 slides ago, Özden, Zeynep, for you, 2
Yes.
slides, previous slides. Yes, you said that, Özden, here is the imbalance fixing my classical question is that, what's the first thing you have to do?
Hocam, collect more data, but hani this was what we had available,
But
and we cannot
always
collect more
mention
data
this.
about.
Don't forget it.
Hocam, I said it, hocam, in the beginning. I said since we cannot collect more data,
Yeah.
that is how I answered.
Ya hocam
the
söyledi.
question.
Okay.
Yeah.
If you go 3
And-
slides back, Çise,
Yes hocam.
you are one more again. You are saying one more again. So
This
you are talking about all, one more again. Columns and rows, columns and rows. Please do not use column. Use
Okay.
feature terminology, feature.
Okay.
The columns are feature. Rows are samples in machine learning. But
Okay.
we represent the data as rows and columns, as table. But the feature is feature, sample is sample. Am I right?
Yeah, you are right.
Okay, and if you go to the beginning of the slides, 3 more. Yes, here you see that, Eray, it's very busy
Yes, sir.
slides. As I explained,
Right.
7 by 7 rule, 7 maximum lines, and each line maximum 7 words, maximum. This is the full paragraph.
You're right. We will consider it after for next presentation.
Go one back again. One more. One more. Is that here? No. Okay. So in the first slide, please provide the project name. What's the project here? Name.
Predictive machine learning for
Okay.
predictive maintenance for
Predictive
Okay.
maintenance.
yeah.
So these are my comments for your feedback. Please take note and improve your project by taking care of them. And please fill in the final report, draft final report already by using these EDA results. Okay?
Okay.
Any questions from the audience?
Hocam, actually, we have questions for you, but maybe after the recording to you, actually. We couldn't decide on something, so.
Okay. Any questions from the audience? Okay. Thank you for the presentation.
Thank you for listening.
Thank you.